Good evening. My NeuralDSP Quad Cortex has an audible defect when I use it for USB audio capture, and today I'm going to use that to illustrate how I debug something. So to understand what the audible problem is, let's hear the same intro music I just played, but this time captured from the Quad Cortex USB. So to be clear, that's exactly the same session. It was recorded using various audio splitters, so that one way it went in through the Quad Cortex to hear that distorted capture, and the other way went through a different audio interface to be captured. Anyway, when I listen to it, the distortion from the QC sounds a bit like digital clipping. So I don't think that's what's happening, but it's pretty easy to go and look and just be certain. So let's do that. As you can see, when I zoom in on the waveform and look at the high points, there's not a flat top there, which is what you would get if it was digitally clipped. So we can conclude that that's not what's happening. So therefore, the amplitude domain of that signal seems okay. Like how high up and down it goes seems to be being recorded accurately. But what about the other dimension, the time domain? Are we getting those samples at the right point in time for it to sound correct? Now, you might assume that the answer must be no, because if we're already saying the amplitude domain is fine. But I'd say we've at this point cleared the most obvious thing from the amplitude domain. There could be some other problem, but let's go and look if we can find a time domain problem, and if we can, we will assume that that is the sole cause of the problem. So, as it happens, I have an application that I use to capture the digital output from all my USB audio devices, and the idea with that is that I start running that application, which captures the USB audio streams from everything. I can loop the cue track for whatever I'm trying to play in some in-ear headphones, and then I can just ignore the computer. I can pick up whatever instrument I feel like using in my little studio here and play it in, and then later I can just find, pretty obviously by looking where there's any kind of noise in that audio stream, the parts of it where each instrument was active. I can then line them up in a audio editor at a later point in time, and they will line up because they were all recorded, or they should line up if everything was recorded perfectly, and then I can make a track even though I was the only one here. Of course, the other reason for the other way I can use that application is if I have some mates around and we all want to have a jam, can pick up multiple instruments at the same time, and then again ignore the computer while we're having fun, but later I can go and edit it together and get the get a complete track to work, hopefully. Now, for that editing to work, the parts all need to have the same sample rate as each other. Some of my audio gear is 48 kilohertz only, some of it's 44.1 kilohertz only. So whatever I was doing, I knew I was going to have to retime the audio from probably the 44.1 devices to be 48 kilohertz, and that's no problem. But I also know from long and bitterly earned experience that clocks can be inaccurate and not meet their specifications. And so just because it says 48K on the interface, I don't necessarily believe that it's going to be 48K. And just because it says 44.1, I don't necessarily believe it's going to be 44.1. And so when I was building the application, I thought, do you know what, I'll just measure exactly what the sample rate my application saw from that device really was, and I can then use that as part of the information for trying to retime the audio. So because I already have this application, I set it up to record a minute of audio at a time from all of the devices that were attached to my that I'd bothered to attach to my computer at that point, which was 8 audio interfaces. I was just looking around and thinking eight seems like quite a lot, but there's another like 7 or 8 on my desk that weren't involved in this experiment. I may have too many, or it may just, you could take the view that there are too many devices that have USB audio interfaces, like game controllers do these days. And anyway, that aside, so I set it up to use 8 audio interfaces, most of which are some kind of like professional music gear. So they should have good clocks. And because I'd been messing around with this for a while, all of those things had been on for like about a day before I started this the experiment I'm going to show you the data for. And so they were, warmed up to the, an even operating temperature, let's put it that way. And I recorded 10 hours of data at 1 minute intervals, so what the sample rate was for each minute. Now, I've said there are 8 audio interfaces. That means there are 9 clocks involved in this game. So there's the 8 one for audio interface, and then the 9th one is the one that's in my PC, which is what I'm comparing all the other ones against. Now, I don't need, because this is all relative measurement, I don't need to assert that my PC clock is perfectly precise and accurate. In fact, I know that it can't be. But because I'm taking all of the audio device clock measurements at the same time versus that same clock, whatever deviation is caused by that clock being inaccurate will be equally showing up in all of the interfaces. So before I even started the experiment, I knew like I'm going to see probably some noise in the measurements because I expect my PC's clock to be less accurate than the best clock in my best pieces of audio gear. Should be the case. But again, it's still, valid, and I should be able to see approximately what that level of noise is at the end in the data. So let me just show you the first crude analysis that I was looking at. So here we have the interfaces, their nominal clock rate. So as you can see, there are 3 that can only do 44/100, and then the rest are nominally 48K. And then here is what I observed as the mean sample rate. And then because this is relative to my computer's clock, and I know that, or I expect that to not be accurate, I don't care that these are not whether they are or are not near the exact number, although as we can see, they're mostly very, very close to the exact number. But what I really care about is the standard deviation. So how much, how variable was the observed clock relative to my PC's clock. So I think my PC's clock is consistent in its idea of what a second is. So it moves at 1 second per second for its definition of a second. And so for the 10 hours of operation, it should be, for all of that time, it shouldn't have huge variation in its idea of what a second is. And we're seeing among the most, consistent audio device, which surprisingly is this webcam I'm talking into you now, that we got, really close to, it was exactly the same audio rate for all of those 10 hours, which is, I'll say, I did expect to see something like this from one of the interfaces. I did not expect it to be from this Logitech Brio webcam. Anyway, so, but immediately you can see I've got beef with these 3, because this is ludicrously bad standard deviation for audio gear. If from 1 minute to the next it's varying by that much, I'm concerned that if I were to, hit record and then muck around in my studio for 4 hours and then hit stop, that during that time I'm going to get such a fluctuation in clock rates that I can't really fix it in post, as it were. So let's dig into what's really going on. And obviously, mean and standard deviation are aggregate statistics. At this point, I think I want to look at some of the actual underlying data. Now, I did this by just staring at the numbers because it was so obvious, but I'm going to show you it in a graph form. So here is what I saw doing a scatter plot for the data from the GM800, which is a synthesizer. So pretty clearly, it's got two modes of operations. Sometimes it will pick to operate at what is nearly exactly 48K, and sometimes it will pick to operate at what is 47,983, and these are in a ratio of about 75% this one and 25% this one. So I can categorize this, like if I say it's less than or greater than 47,992, I'm going to split those two modes data extremely cleanly, and I regard that as fair to do, because the behavior of this device appears to be, when I start recording, it picks a clock rate. It will be one of these two, and it will stay locked on that for the duration of the recording. If that weren't the case, we would see data points in between. So I'm happy with the assertion that I can split this into its two modes of operation, and I will have to record which mode of operation it ended up using so that I can correct the timing of it if it picks the low rate. But I was planning to do that anyway, so this is actually not going to be a real problem for me. Now let's look for the GP10, which is another kind of synthesizer, and from the same manufacturer, as it happens, and it's just like 20 years of time difference between them, but it has exactly the same kind of behavior. Sometimes, in this case, I think it's 2/3 of the time, it picks to run at almost exactly 44,100, so slightly fast, but almost exactly its target number. And sometimes it picks to run at a bucket higher than that. But again, if I were to cut these anywhere in this range, so I think it's 44,109 looks like the midpoint, I'm going to get a clean separation of those two modes of operation. And again, it appears that once it's picked a mode, it stays in that for the duration of a recording session. So pretty good. Now let's look at the same kind of graph for the Quad Cortex. I don't see any it's clearly not the bimodal thing that we were just seeing. It's also very concerning that the target clock rate isn't even on this graph. We're 20 hertz below 48K at the highest clock rate we saw. But I can't see it's clearly not the same very clean bimodal split as the other two, but it could still be a properly multimodal split with there could be 10 modes here, and I think it could look this chaotic. So in order to eliminate that, I took the data for the observed sample rate, ordered it by descending observed sample rate, and plotted it in a different way to have a look at it. And that's this chart here. And I'm not seeing clean steps. Like the steps you can perhaps see in the video are artifacts of the rendering accuracy of this monitor at this zoom level. It's not there's not really steps there. It's essentially a continuous S-ish shaped curve, and that's really bad because I can't correct that. I have no reason to believe that this sample rate that got used for this session was constant for that session and would have remained constant at that session. In fact, from other measurements I've done, I have good reason to believe that that's not the case. So from the audio point of view, this is a terrible clock to be trying to deal with. But from the alternative point of view of trying to work out why the captures from my Quad Cortex sound bad, this is a huge clue potentially, because what we have here, well, we can assume that perhaps it sounds bad and this are some relation to each other. Now, like, as I'm speaking to you, I know what that relation is, but when I first was looking at this data, I didn't. So I'm going to try and take you through how I got from knowing this was happening to, and that it sounded bad, and I needed to explain that, through to the conclusion I reached. So it's going to help us to look at a very basic chart of what's involved in the signal chain. So at one end, I've got a guitar. Into that's plugged a cable that goes into the Quad Cortex's input socket, which is then converted from analog to digital. That's what ADC means, analog to digital converter. That signal is then logically split inside the Quad Cortex. So one part of it goes straight to the USB output as what's known as a dry signal when you're doing this audio stuff, and the other copy of it gets sent to the Quad Cortex's DSP engine, which simulates various guitar effects and amplifiers and whatever, and creates what we call in the business the wet signal. So if I use dry and wet later, you'll know what I mean. That also gets sent to the Quad Cortex's USB out, from where it goes into a USB cable that goes into some chain of hubs and other cables potentially. Like there's still manufacturers will still put in the manual, plug it into a port on your motherboard as though that's a real USB port. That hasn't been true since the 1990s. On my motherboard, there are several USB hubs, and there's USB cables that are just traces in the motherboard that go to where the actual USB controller is. So that this USB cables, etc., is doing there's a lot of hidden complexity here, and that might be one of the if we determine that the problem is in there, that would be a real pain in wherever your culture traditionally has pains. Let's go with neck, because I'm trying to keep this family friendly. Then we have the PC hardware. So there are USB controllers, multiple USB controllers in my PC. Some are on the motherboard supplied by the motherboard vendor. Some are in the chipset supplied by the chipset vendor. Some are in the actual CPU itself. And then we have the operating system that I'm using. And then on top of that is my recording software. We'll start with my software. I'm going to say, because the other 7 audio interfaces, which are plugged into the same software, are fine and sound fine. And also because when I use other recording software that I didn't write, I hear the same distortion. Now, those other pieces of software don't record the actual clock rate, so I can't confirm the clock rate problem is there on all of them, to be clear, but I can confirm that the audio distortion is there on everything, and I'm assuming for the moment that those things are related. So that's why I say I don't think the clock rate observation is caused by my software, because if my software were wrong, I would expect the same amount of error to show up in the other audio interfaces. Let's look at why I think I can eliminate the operating system. Well, because I've dual boot this machine between Windows and Linux, and I hear the same distortion on either side. So as it happens, I'm using Linux to do this analysis because it's easier for me to be absolutely sure that the drivers are correct and everything on Linux. But I had the same distortion problem on Windows and as I do on Linux. Now, At the other end of things, I can eliminate the guitar because, well, the most obvious thing to do is just plug it into another interface or to a guitar amplifier and see if you getting sort of crackly distortion things. It's not an insane thing to test because you certainly can get distortion on the guitar, and it's also very important that you could get distortion with a guitar because of its construction that only occurs when it's plugged into one kind of amplifier. So to eliminate that, what I've used is a device called a buffered splitter to plug my guitar as the input of that, and that gives me two outputs from that buffered splitter at the same time. So I take one into the Quad Cortex and one into another audio interface and record them both at the same time. So because the recording from the other audio interface is clean, I think I can eliminate the guitar and that side of the buffered splitter as being wrong. And then the second part of that test is to swap the cables. So the one that was going to the QC goes to the audio interface, and the one that was going to the other audio interface goes to the QC. And I still get the same result, that the other interface gets a clean recording and the QC is distorted. So it does not matter, but I can eliminate from my inquiries the buffered splitter and all the cabling, because whatever I do with those, I get the same result, that the QC is distorted and the other interface is clean. So that is, again, why I'm eliminating that. Now, simple to eliminate the PC hardware is a little bit annoying. It was go and get another computer, test if you hear the same distortion. Yes, I do. So this is for the PC hardware, like as a gross, wholesale thing, not specifically the USB parts of it. We will come on to that. So happily, the Quad Cortex needs the same kind of USB plug plugged into it as several of my other interfaces. So what I've done is unplugged the USB cable from one of those other interfaces and from the QC and just swapped them. So I made no other changes. I didn't change what port anything was plugged into. I didn't do anything. Just literally the cable at the interface end I unplugged and plugged into the other device. So I swapped initially the Quad Cortex with the GM800, ran the same measurements. Again, I get bad clocks and distorted audio from the Quad Cortex and good clocks and clean audio from the GM800. Swapped them back, and then I did the same swap but between the Quad Cortex and the Pod HD Pro. So, and again, I get good clocks from the Pod HD Pro and I get bad clocks from the Quad Cortex. So whatever USB path is involved for those two, and I did look in the USB tree viewer that they are going through completely different controllers on the motherboard and completely different chains of hubs and so forth to get back to the computer one way and the other. It doesn't matter where I plug the Quad Cortex in, it sounds distorted, and it doesn't matter where I plug the other two devices in, they sound fine. And I wanted to be very fair about it, which is one of the reasons why I swapped with the GM800, because the GM800 requires more USB bus bandwidth than the Quad Cortex does. So that also kind of eliminates its bandwidth congestion, and because the Quad Cortex has more USB channels than it has more USB channels than the Pod HD Pro, but it has fewer than the GM800. So it isn't that. Okay. So now, can I eliminate any of the parts of the Quad Cortex? Well, what you heard in the intro music was audio from the Quad Cortex, but from its analog output, not from its USB output. So the Quad Cortex input analog to digital converter and the DSP engine must be okay for that to sound good. And also, as it happens, the Quad Cortex output digital to analog converter must be okay. So all of those three are in the clear, because if any of those three was causing a distortion, I would hear it when I capture its analog output. And so that is primarily why these two are in the clear. I'd sort of penciled in that the DSP engine wasn't a problem because there's a clean output, a dry output on the Quad Cortex USB, and that is also distorted in the qualitatively in the same way as the wet signal is distorted. So my conclusion is that inside of this component, like isolated to the part of the Quad Cortex that produces the USB output signal, there is something causing this distortion and this bad clock. And now I'm going to talk about the next level of experiment. From here on, I'm making the assumption that the Quad Cortex is intending to hit 48 kilohertz sample rate. And secondly, at the times when it does hit 48 kilohertz sample rate, the signal is clean and undistorted. So if I take that assumption, then what that means is that the apparent low average clock rate is because some samples are missing, like are never sent, or at least never received by my computer. So they never transfer from the Quad Cortex to my computer. And that ratio to get the sample rate I'm seeing would mean about 1 in 200 samples on average have to go missing. Now, I could think of two obvious ways that samples could go missing. You could miss like one time slot's worth of samples, which would could be explained by perhaps a mismatch between the clocks for the DSP section and the clocks for the USB section, so that the buffer isn't valid when it goes to read something from the DSP and it just skips a sample. That's something I could conceive of happening inside there, because I've obviously no idea how the code actually works. Or the next most obvious thing is for a USB transfer-sized block of samples to go missing at a time. And I had a look at the USB descriptors for the Quad Cortex, and it sends 8 samples per isochronous transfer block. So we should be missing either 1 at a time, or 8 at a time, or perhaps 16 at a time, because blocks tend to be in pairs. So I wrote a program to corrupt the audio from one of my other audio interfaces by throwing away, by rolling a dice, and for every sample, 1 in 200 chance of just throwing it away, to simulate the one sample at a time goes missing conjecture. Now that made the audio sound a little bit sharp because it plays back slightly faster than it was recorded at, but it doesn't actually sound distorted. It's like I wouldn't know from listening to it that it wasn't just recorded slightly on a slightly out of tune sharp guitar, or that it wasn't just sped up slightly by 0.5%, right? Which is interesting. I hadn't predicted that. If I predicted that, I would have probably not bothered with the experiment. But when I started to change that code to say, well, like assume a block of samples is 8, a group of samples come in groups of 8. For every group, roll the dice and 1 in 200 times throw it away. At that point, I was hearing the distortion, qualitatively the kind of distortion sound that I've been hearing from the QC. So it doesn't sound dramatically different if you drop blocks of 16 instead of blocks of 8, unfortunately. But I'm willing to say it is not. This is not caused by a 1 in 200 chance of losing one sample. This is caused by a roughly 1 in 200 chance of losing a USB block of samples. And that is why the Quad Cortex USB capture sounds bad on my Quad Cortex. So that's interesting because there's an obvious hardware possibility for that kind of thing happening, right? If the Quad Cortex has a weaker than usual USB line driver, then it wouldn't, so it's not driving the differential pair with enough distinction. It's not creating those data eyes that you should get when you look at it with a high frequency oscilloscope and protocol analyzer. If that's what's going on, then I should be able to see that either by getting a fancy high frequency oscilloscope and looking for the data eyes, which I don't own one of those and I don't feel like hiring one. But the other thing I can do is look at bus level packet capture from my PC using Wireshark. And the reason that that's going to work is if we're saying that if the conjecture is that a line driver error is causing 1 in 200 of these USB packets to appear malformed when the hardware checks for CRC errors, so it throws them away, and that's why we're missing packets. For that conjecture to make sense, you'd have an equal 1 in 200 chance per USB packet that it goes missing. And the reason you can see that in a host bus level capture is because you would still get the out of sequence. So USB isochronous data packets have what's known as a data toggle. They get described as data 0 or data 1, and they just strictly alternate. So if we are corrupting packets at random with a 1 in 200 chance, there's basically no way I'd be able to capture hundreds of thousands of packets and not see a data 0 followed by a data 0 or a data 1 followed by a data 1. So I did this experiment. I captured a massive sequence of packets. I verified that during that capture, the clock I was seeing from the Quad Cortex was in one of its bad regimes. And then I looked for data toggling errors in the isochronous data from the Quad Cortex, and I didn't see any. So this doesn't rule out all classes of hardware error or anything, but it does rule out the sort of basic line driver is not doing the work conjecture, at least for me. However, there's plenty of other ways to create a problem where a USB packet-sized group of samples goes missing. Firstly, I have no information on how QC works internally. That USB packet size might be the same as the simulation packet size, so it could be that it's still in the handoff from the DSP to the USB section that we're losing data, and we're losing a whole group at a time, and that's because that's the group size from the DSP. It could be just the sort of ring buffer management problem. It could be a bad clock smearing algorithm. It could be a otherwise good clock smearing algorithm, but with a loss of floating point precision. It could be that we're trying to match two clocks and one of them's out of the range where it's thermally it's got too hot or too cold, but usually too hot. It's got too hot to be stable, and the temperature compensation isn't doing its job well enough. It could be any number of other problems, and it could be across the hardware of the device or across the firmware that the device is running. Obviously, I would really hope that it's a firmware problem and that it can be just fixed with an update. But, hope is not a reason to make the assumption that reality is like that. So anyway, here's where I end my debugging. I can't do anything more to debug this. I'm short of, well, without disassembling the device and attaching high-speed oscilloscopes to various internals of it. And even then, like, it's probably not something I'm going to be able to fix without writing custom firmware for it, which I just don't want to do. I'm going to pass all this information on to NeuralDSP and see what they want to do about it. To be totally transparent with everyone, I've owned this device for many years. If there's a limited time warranty, it's almost certainly out of that limited time warranty. I didn't buy it in the UK or EU, so I don't have the standard broad consumer protections that we get, having bought it in the US. And yeah, so I'll just ask them what they would like to do about it, if anything. If they, the thing is, I've got very adequate workarounds for it. So if it's going to cost me money or time without, significant money or significant time without the device to have them look at it, I'm not particularly keen to do that, because I can achieve the same end by taking another analog out from the Quad Cortex to my other interface and just recording that. So, but anyway, if as I say, I will contact NeuralDSP. If they tell me anything I can share, I'll put it in a comment on this video. If it ends up being a firmware update that fixes this because it's a problem affecting all units, then I will also put that in a comment. If my account is allowed to pinned comments, that comment will be pinned. I actually never tried pinning a comment, so I don't know what the rules are. And anyway, I hope this trip down debugging avenue has been interesting to you, whether or not you're into your music gear. And I will see you in the next episode. Cheerio.